Welcome to MegaMechanism1b. In this mechanism, we're going to explore the sequence of reactions that converts this secondary alcohol that also has a ketone using triisopropyl chloride and imidazole to form a protected alcohol, which then undergoes a condensation reaction of the ketone to an imine The next step involves using tetrabutyl ammonium fluoride to deprotect the protected alcohol in the presence of methanol, which also serves as a proton source as well as the solvent. Next step involves using chromic acid to convert the secondary alcohol to a ketone. Acetylide is the nucleophile that will react with a ketone to create a tertiary. Propargylic alcohols are analogous to allylic alcohols. In the mechanism, the first step, triisopropyl chloride undergoes ionization because silicon is less electronegative than carbon, so it generates an even more favorable cation than would be a tertiary carbocation. This cation attracts the lone pair of the alcohol with a mechanism like this. This arrow clearly needs a little help. We generate this intermediate here, an oxonium ion, which will be neutralized using the scavenger, the proton scavenger, imidazole. Bear with me as I fix this arrow here. Here's the neutralization step, which generates your protected alcohol. Next, the ketone is going to react with the primary amine in the presence of a Dean-Stark trap to make an imine. Reminder, Dean-Stark traps help all condensation reactions, of which this is one. The lone pair on the nitrogen, as you know, is a pushy fellow. It will attack the carbonyl, generating an alkoxide, illustrated here. The O- cannot reach the H, but acid-base dictates that the O- being a conjugate base of an alcohol and an ammonium ion having a pKa of 10, they must undergo an acid-base reaction, where 10 goes towards 17 in terms of pKa. Cannot reach because the ring size would have been 4 if they tried to grab each other in one step. So intermole means the O- grabs the H from a second identical molecule, thus generating this intermediate, which we call an aminol. It's got an amine and an alcohol. Nitrogen's got its lone pair back. It is pushy enough to kick off even a lousy leaving group such as hydroxide, as illustrated here. The iminium ion, thus generated, is neutralized by the hydroxide ion in an acid-base reaction, thus giving the imine illustrated above. Next step, we're going to deprotect our triisopropyl silyl ether protected alcohol using tetrabutyl ammonium fluoride, which contains the very reactive nucleophile fluoride. One of the strongest bonds possible on the periodic table is a covalent bond between fluorine and silicon. That is the driving force of this reaction. We generate a pentavalent silicon. Silicon is able to do this being in row 3. This species will now ionize to the more favorable O- instead of Si-, thus rendering triisopropyl silyl fluoride and the alkoxide ion indicated, which will pick up a proton from the solvent, giving us our secondary alcohol, illustrated to the right. Next step, chromic acid oxidation of a secondary alcohol to a ketone. Lone pair on chromium, oxygen, chromanyl, will be used. The secondary alcohol will be the nucleophile, which is not a very good nucleophile. So we must activate the chromium oxygen first. This is accomplished using sulfuric acid in a protonation step. Thus generating the species illustrated below. The protonated chromanyl is reactive enough to react with even a weak nucleophile such as an alcohol. Attack the chromium. Pi bond breaks, giving oxygen its lone pair back and giving it a 0 formal charge. Alcohol now has an oxonium ion, which must be neutralized. I realize I made a mistake on the formal charge here. Sardu wants me to fix that. There you go. I fixed it. And we neutralize our oxonium ion. This generates what we call a hydrate of a chromate ester. Remember, a chromate ester looks like chromic acid with a carbon attached instead of an H. Chromic acid illustrated up here. Lone pair on bisulfate picks up a proton. Sigma becomes pi. We must make OH a better leaving group by protonating it with sulfuric acid. And this is a classic E2 reaction. When we have E2 of water, we call it dehydration. And we have a chromate ester. This H I'm circling here has been there all along. It must be lost in the oxidation step to generate intermediate X, molecule X, which I have shown above. This is the oxidation step. We'll see X shortly. Oxidation is accomplished using the lone pair on the oxygen of water, which we generated in the previous step. In an elimination fashion, we grab an H. Sigma between C and H becomes pi. Chromium gets reduced by gaining electrons. And carbon gets oxidized by gaining a bond to oxygen. Species X here is really species X here, which is clearly a ketone on top. Acetylide ion has a spectator ion. It's a strong nucleophile, and it is attracted to the carbonyl carbon of the ketone. It will be attacking that carbon shortly. Don't like that arrow. A little better. We're going to be generating an alkoxide ion, which in step 2 will become an alcohol because this is the conjugate base of an alcohol. Step 2, HCl workup gives us an alcohol, which you can see is called a propargylic alcohol. Propargylic alcohols are like allylic alcohols. I realize now we have room for more mechanisms. So I'm going to do oxymercuration protonolysis of a terminal alkyne as we studied in chapter 7 to generate a ketone. Here's your terminal alkyne, here's your ketone, and let's do it. Alkyne pi electrons are strongly attracted to the strong Lewis acid mercury 2+. They will be generating a cyclic intermediate, illustrated below. It's a cyclic mercurinium ion with the cation on mercury and another cation shared by all 3 atoms in the triangle. Every time we generated a triangle in organic 1, we popped it open using a backside attack. That has not changed in organic 2. It doesn't look like a backside attack to me. I think I'm going to change things around a little bit. Move the water over and attack from the backside of the mercury bond. Notice the product is anti. That is the result of a backside attack with the O on one side and the mercury on the other. Oxonium ion is going to be neutralized, as we often do, using a base. Sulfate ion, not bisulfate. We had sulfate with our mercury. It is a better base. It's the conjugate base of bisulfate. Here's the neutralization step. Generating this species here. Mercury plus attached to carbon is going to undergo a protonolysis reaction using sulfuric acid. We haven't used sulfuric acid yet. Very strange to see such a reactive species not react until this late in a mechanism. That is a testimony to how reactive mercury 2+ was early on. Protonolysis gives an enol, an alcohol attached to an alkene. Enols will undergo tautomerization using a base, bisulfate, and its conjugate acid partner, sulfuric acid. Base grabs the H. Sigma becomes pi. Alkene pi electrons protonate, generating a CH3 on the end, thus giving us this species here. I've relabeled R prime. It is now our job to see that the imine is also undergoing a hydrolysis reaction under the same conditions of the oxymercuration protonolysis. We are getting our ketone back from the original ketone on the start of our whole scheme here. Water is not that attracted to the C-double-N because it's not a very polar bond, but in the presence of a strong acid like sulfuric acid, which would protonate, this reaction occurs. Not happy with the way that looked. So really I would think that the protonation step would be the leading step and the attack by the water would follow quickly thereafter. Generating this oxonium, which must be neutralized, that would be a step illustrated here. And a completely separate step to set up the next part of the mechanism would be protonation of the nitrogen to make it a better leaving group. These are clearly two separate things, so I gave them different colors, and they gave this intermediate here, which is an alcohol on the same carbon as an ammonium ion. If we do a simple deamination, which is like a dehydration, but we're getting rid of an amine in an E2 fashion, I believe we end up with our final product. And the amine leaves as it picks up a proton to make it a better leaving group. And that's the end. In summary, we have a secondary alcohol. It undergoes protection with triisopropyl silyl chloride, generating this silicon cation. Imidazole neutralizes the oxonium. Then we form an imine by reacting a primary amine with a ketone, getting an oxide ammonium intermediate, which undergoes intermolecular acid-base proton transfer, giving this aminol intermediate, which undergoes an elimination to form an iminium ion. The iminium ion is neutralized by the leaving group hydroxide to give the imine. The silicon protecting group is removed with the fluoride anion, generating this pentavalent silicon intermediate, which ionizes to this alkoxide, which protonates using the solvent methanol. Here's our deprotected alcohol, and it's going to undergo oxidation with chromic acid in the presence of sulfuric acid in an aqueous environment. Protonation of the chromonyl gives a chromonyl oxide, which undergoes attack by alcohol to give this oxonium, which is neutralized to give this hydrate of chromate ester, which undergoes oxidation to form our ketone, X. Acetylide attacks ketones, as we saw in chapter 16. Second step, protonation of the O- gives a propargylic alcohol. That's new for us. Reaction of the alkyne with mercury 2+ cation generates a cyclic mercurinium ion, which undergoes a backside attack by water on the more substituted carbon to generate this oxonium, which is neutralized by sulfate, which undergoes protonolysis to give an enol, which undergoes tautomerization to give our ketone, and the imine undergoes hydrolysis using water and sulfuric acid to give first this oxonium intermediate, which is neutralized, and an amine which is protonated to make it a better leaving group, which undergoes deamination in an E2 reaction to generate our final ketone. Thus concludes our reaction.